In this video, you're going to learn the engineering principles behind a Cripple wall retrofit. If you don't know what a Cripple wall is, please click on the card above. This video is also an introduction to the seismic retrofit of single and two-story dwelling calculations that were done as part of Standard Plan A, a regional guideline here in the San Francisco Bay Area. These calculations are about 80 pages long. There's a whole lot there, and if you understand how to use these calculations, you'll be able to do anything on your house or anyone else's house for that matter, because this is actually the foundation of every single retrofit. This is the science. And once you know the science, then you can apply that science to any house that you want to protect. So anyway, let's go ahead and see what the introduction here is and get the basic concepts. And then towards the end of the video, we'll go into this right here. Now, it's important to know what types of tools are available. If you don't know what types of tools are available, you don't know what sort of things you can actually do if you need to. So you need to keep up on the tool development. Changes all the time. They're always coming out with new tools. The other thing that's important is you need to understand what type of hardware is available. What types of bolts are there? What types of fasteners? What type of screws? Which ones should be used when? And you also need to know, basic construction methods, from a practical point of view, how's the best way to just build something. So if you want to learn the practical part in terms of the tools and the type of hardware that you need to use, the best place to find that information is through the San Leandro Retrofit Workshop. It's held, every couple of months. And the way you find out about it is you go to our homepage, you get resources for homeowners, down to preparedness, then San Leandro's Retrofit Workshop, click there, and you go to the Retrofit Workshop link right here, and it'll tell you all the days and times that they're having their next one. Now this is led by their chief building inspector, who's very, very good at what he does, and it also has two other very experienced inspectors who do it. They've seen this stuff lots and lots of times. They know exactly what they're doing. They have all the tools that you can rent. They have all the hardware to look at. So if you want to know the practical part, this is the place to do it. Now, on the other hand, you need to understand the science. And that's what the engineering is. You can do a whole lot of work, and we see it all the time, a whole lot of work, and you do high quality work, except because there was no understanding of the science behind a seismic retrofit and what happens to a house when there is an earthquake, you can end up spending a lot of money on very high quality work by a very honest contractor who would never cheat anyone in the world. And you can pay him a whole lot of money and you won't get anything for it. There was an article in the New York Times all about this. You can also get an engineer who doesn't understand the practicality. So we've had engineers who have asked us to do things that are literally impossible because they don't make a tool that can do that. We've also seen engineers make things up. That what happens is they just think about, well, what happens to a house in an earthquake, and then they'll start putting, fasteners, they start connecting the roof to the walls and things where there's never been a failure ever. And they'll go ahead and reinforce those connections, and that makes it outrageously expensive. One thing about engineers I've seen a lot of, they don't have any sense of cost, for the most part. They don't have any sense of cost, so they come up with these designs that are so expensive, they simply can't afford them. And someone will pay for an engineer to, a couple $1,000s, and then he'll get a design, and then nobody can afford them. And then the person ends up, spending a whole bunch of money for an engineer for nothing. So let's go ahead and look at the basic engineering concept so you can tell if your engineer or your contractor knows what they're doing. When talking about earthquake forces, we refer to pounds of force. So let me explain how that works. What actually happens in an earthquake is the ground moves underneath the house like that. So the foundation and everything just goes like that. And then inertia wants to pull the house back like that and cause it to slide from its foundation. Now that is exactly the same as something pushing on the house. So let's assume that you have something that weighs, let's say it weighs 10,000 pounds and it's pushing against the house, like this. that is the same as a ground acceleration measured in G's underneath the house. So we're actually looking at a ground acceleration under the house, and we're translating that into pounds of force that are attacking the house. So what it is, when we're looking at hardware and we look at anything else, we look at them in terms of pounds of resistance. So you're going to see references to different types of hardware, to houses being attacked by a certain amount of force, and that's what it means. So this is how you design a retrofit. The first thing you do is you calculate the amount of force that's going to strike the house and at the base, and that's called base shear. That's where all retrofit engineering, all retrofit design, all retrofit practice, all of it should begin. If we don't know what the force is that's going to attack the house, then how can we design around it? So that's the number one thing, is we need to know that. So once we calculate the earthquake force that is going to attack the house, we use that to determine the amount and number of retrofit components we're going to need to resist that force. So the first thing we're going to do is figure out how much earthquake force this hypothetical two-story house is going to need to resist. We use those calculations to figure out that there will be 0.2 Gs is the anticipated ground acceleration underneath the house. So basically the house, all the force is going to happen underneath you, because that's what happens. The ground just accelerates very suddenly, and according to those calculations, at least what we're looking at is 0.2 Gs. Now our hypothetical two-story house, it weighs 80 pounds per square foot, and this house is 1,000 square feet. Now we take that 1,000 square feet, we times it by 80 pounds per square foot, and we get 80,000 pounds. So that means that this house weighs 80,000 pounds. And so we take the earthquake force is going to equal 0.2 Gs, which we figured out earlier as the anticipated ground acceleration, times the 80,000 pounds, and that gives us 16,000 pounds of earthquake force. So if we were going to define this in some way, what we would say is that there's a very large vehicle and it's right up against our house. It weighs 16,000 pounds and it accelerates very suddenly at 0.2 Gs, tries to knock the house off. And we need to put enough retrofit components to resist that force and keep our house on its foundation. And we're going to go see exactly how to do that right now. Earthquake forces attack a house equally in all directions, regardless of which way the fault runs. So in our hypothetical retrofit here, we have 16,000 pounds coming this way. We're going to have 16,000 pounds coming this way. We're going to have 16,000 pounds coming this way. And we're going to have 16,000 pounds coming this way. Now this right here, we have 16,000 pounds coming here. Half of the force, or 8,000 pounds of force, is going to come along this wall. We're going to have 8,000 pounds coming on this wall. So on those two walls, we need to have enough plywood, bolts, and shear transfer ties to resist 16,000 pounds of force. Now the same thing, earthquake force is coming in this direction. We're going to have 8,000 pounds of force on this side, 8,000 pounds of force on this side, which equals our 16,000 pounds of force that we calculated in our calculations. So on this side, we're going to need to resist 8,000 pounds of force, this side 8,000 pounds of force. So on each side, we need to put in enough bolts, enough plywood, and enough shear transfer ties to resist that force. Now every bolt, every type of hardware, every linear feet of plywood can resist a certain amount of force. So we just need enough to resist 8,000 pounds of force on each side. So we're bracing this house. It's a Cripple wall retrofit. So remember all these things. We're going to be bracing the Cripple walls with plywood. Next component is we're bolting the Cripple walls to the foundation. And the third thing is we're attaching the floor to the bolted and braced walls. And so the plywood on the Cripple walls will need to resist 16,000 pounds of force. The bolts on the Cripple walls will need to resist 16,000 pounds of force. And the shear transfer ties will need to resist 16,000 pounds of force. So once we've done that and all the connections that can possibly fail have been reinforced so that they can resist that 16,000 pounds of force, we can call our house fully retrofitted and we don't need to worry about it when the earthquake hits. So let's go ahead and see how we figure out how many linear feet of plywood we're going to need. So our plywood can resist 571 pounds of earthquake force per each linear foot. We need 14 linear feet of plywood on each side to resist 16,000 pounds of force each direction. So what we've done here is we simply divided 16,000 pounds by 571, and we ended up with 28 linear feet. So half of that linear footage is going to go on this side. Half of that linear footage is going to go on this side. Same thing for earthquake forces coming in this direction. Half the linear footage is going to come this way, and half the linear footage is going to come in that way. So we figured out that we need 14 linear feet of plywood on each side, and that's all we're going to need. So now we need to figure out how many bolts we need to attach the mud sill to the foundation. We do the exact same thing we did with the plywood. What we do is we take the anticipated earthquake force, which is 16,000 pounds of force. We divide that by the earthquake resistance of a bolt, which happens to be 1,142 pounds, and then we come up with 14 bolts. So we need 7 bolts on each side of the house. So earthquake forces coming in this direction, 7 bolts go on this side, 7 bolts go on the other side. Earthquake forces coming in from the other direction, we need 7 bolts on that side, 7 bolts on this side, and that's how you figure out your bolts. It's very simple. Now we do the exact same thing for the shear transfer ties. Shear transfer ties can resist 571 pounds of earthquake force. So what we do is we take the 16,000 pounds of earthquake force that's going to attack the house, and we divide that by the 571 pounds. And that gives us 28 shear transfer ties. Now that means when 16,000 pounds of force attacks the house in this direction, we're going to need 14 shear transfer ties on this side and 14 shear transfer ties on that side. And when 16,000 pounds of earthquake force attacks from this direction, we're going to need 14 shear transfer ties on that side and 14 shear transfer ties on this side. So now we have our bolts, we have our plywood, and we have our shear transfer ties. And we're going to look right now at how it all comes together. So this is what our final design looks like. I'd like to go over the legend first. So this pink dot right here, that's a bolt. This green line is plywood. And this is one of the shear transfer ties we looked at. And so if you'll notice, we have 14 feet of plywood on this wall. We have 7 bolts, and then we have 14 shear transfer ties. We have the exact same thing over here, exact same thing over here, and the exact same thing over here. That's because we want to have equal resistance on all sides. Now remember, this house is going to be attacked by 16,000 pounds of earthquake force on each side. So we have 8,000 pounds on this side, 8,000 pounds on this side to equal 16,000 pounds. We have 8,000 pounds on this side, 8,000 pounds on this side, also to equal 16,000 pounds. I'd like for you to notice that these bolts are all right next to the plywood. You see the plywood is here, and then all the bolts are right where the plywood is. And that's because all the earthquake force goes into the plywood. Only the bolts attached to the plywood actually do anything. When you see a job where they're saying every 6 feet or something, that's completely wrong. You just put it where the plywood is. The other thing is you want to make sure that your shear walls are in one piece as much as you can. That reduces overturning. If we put, say, 7 feet here and 7 feet here instead of 14 feet right here, we'll probably have to deal with overturning on this one, and that will require more work and more hardware. Earlier I mentioned that I would go over the calculations from Standard Plan A, which are the basis of the retrofits that we do anyway. Now we don't use the practical part of Standard Plan A. It really has a lot of flaws, but the engineering is excellent. I knew the engineer personally, I was on the committee, and he actually gave me a copy of those calculations. And he also taught me how to apply them. So I know these calculations very well, and I also know how to use them. So let's go down and see what's actually in these calculations. The first part is pretty much all the geology. So, this is, geology is really important. There was a geologist on the committee who told us, which geology we should use. And so that's what you're seeing there. So the most critical part of this whole this document, or at least what makes it the easiest to work with, is this right here. So you see where it's A, B, C, D. Now that has to do with the types of houses. So for example, type C, it says lightweight roofing, cement plaster or stucco, exterior finish, and gypsum lath and plaster interior finish. Now that means a typical house with composition shingles, and then it's got stucco on the outside, and the older houses don't have sheetrock, they have plaster. So this is a particular type of house. And then there are the other types of houses that you see for A, B, and D, and you just read, and they're self-explanatory. So we use that as our baseline for the weight that we're looking for. Now we go down further, and then we can make allowances for different things. We can, the rafters and does it have sheetrock on part of it, and how about the carpet, and how thick is the wood flooring, and all these other things. So these are also variables in the engineering that we need to make account for. So if we look at all these engineering calculations right here, so they just go forever and ever. There's about 85 pages worth, and if you take the time, you can learn this stuff, and then you could apply it to your own house. Probably better just to hire someone who knows how to do it. Like for example, we can just do it, with no time at all. We're just used to doing it so much, rather than trying to do it yourself. If you could comment on this video, it would be greatly appreciated. If you have questions, someone else will have questions, and sometimes we can get into some pretty good discussions about retrofitting where everybody benefits. It's also good for me to hear from you. Sometimes I feel like I'm making these videos and there's no one on the other end, so it's just good for me to hear that I'm doing something valuable for people. So anyway, I do hope to hear from you.